Thank you for the introduction. So I will be talking today about neural networks and their applications to natural language processing. I hope that it will be not such a big magic in the end, because we actually understand pretty well what these models are doing, and I would say that there's definitely much more machine learning than artificial intelligence. Although that's our big goal, like how to develop some really like intelligent models of the language, but we are like far from it, and we have just what we have. So for the introduction, of course, like we have seen plenty of applications before in the previous presentation of neural nets to tons of problems. Here I have a few of them that involve language. We did see, for example, the example about web search, where neural networks can be a very useful signal that's used to be complementary to the others to improve the quality of the search results for the real users. Across like not just Google search, but even other companies are of course working on the same topic. Then there's advertisement, where there's also like either language data, or we can actually deal with the ads in a similar way, like treating them as some discrete tokens and building their representations. That's actually a pretty big deal, because advertisement is actually how companies like Facebook, Google, and others are making like more than 90% of the money. So it's actually a very important task as well. And then the spam filters, that's another like super important topic. Like just imagine how your email inbox would look like without good spam filters. Of course, the text classification is just one component there, but it's a pretty important one. And then machine translation, again, is like a very nice task that is making life of many people easier. So I will be talking today about more like details, not just this high-level overview of these applications, but how can actually people here use neural networks to build representations of the text in unsupervised way and also in supervised way, and how to use it for like practical tasks like classification. And then the second part of the talk will be about recurrent networks, where we are using this very simple concept to understand that it's basically weight sharing, and that's behind much of the success in the last years of the so-called deep learning. So the first part will be really like the simpler one. That's about the distributed representations of words. It's actually pretty easy to understand the techniques here, and there's tons of applications. So I think that people may be interested in this. I will also say something about the FastText library that we are developing at Facebook research group, and that's basically a follow-up project of the Word2Vec that has some extra functionality and can achieve somewhat better results. So word vectors are like some like very basic component in most of these NLP applications, where we start with some basic representation of text, where we build a vocabulary, and each word is associated with a unique entry that is orthogonal to everything else. That's the so-called one-off encoding. But that completely ignores the fact that similar words should be sharing some properties, and the model that is built on top of the one-off representations needs to recover information like that. For example, France and Italy are similar words, and that they should be like training a little bit like together. So the success of the word vectors is through the unsupervised pre-training, that we can actually take tons of text data. You can think of, for example, the whole English Wikipedia, and train these word vectors on this unannotated data set, and then use them in some supervised classification tasks where we have small amounts of labeled examples, and this way you can actually obtain much better generalization through that unsupervised pre-training. One can see that there are some similarities to the word classes that can be also pre-trained unsupervisedly, and that were very popular in the NLP field also like for many years. Word vectors can be seen as a generalization, because unlike the word classes, there's no concept of like word belonging to a class or not, like there's no discreteness. The words are really represented by some continuous vectors. You can think of like 100-dimensional float vectors. And as I said, similar words after successful training will have similar vector representation. These can be used in many NLP tasks like name identity recognition, part of speech tagging, text classification, and so on. And that has been shown already like in 2011 in Ronan Colobert's paper. And the main usefulness of the word vectors back then was by providing the generalization, as I was saying, by pre-training on huge data sets and then using these pre-trained word vectors in tasks where there was limited number of labeled examples. But of course, one can also like get some more insight into what the data are about, and one can apply the same techniques even to representing, for example, user queries in search engines, and that's actually what was also done. When I started working on this topic, that was like a long time ago, but what I didn't really like very much was that the machine learning community was proposing more and more complicated ways how to train these word vectors. They used to be called deep embeddings at some point, and people were making claims that you really have to train some really complicated language model, like say a recurrent one or convolutional, to train good word representations. And then people trained their models like on different data sets, compared them on a supervised task where they used the word vectors just as pre-trained features. And it was kind of like such a somewhat different state of the research where it was very difficult to figure out what actually works and what are the important components of the architectures that were used to compute these word vectors. So actually at Microsoft Research and later at Google, we were developing data sets that can be used to measure the quality of the word vectors that would be somewhat task independent. It started with this interesting observation that actually it made originally for the Czech language already back then in 2007, but in English I think it's looking more impressive because not many people speak Czech here. And the example goes like this, that you have basically in this vector space, as I said, it can be like 100-dimensional space, so this is just illustration examples that we did right by hand. You have basically these subspaces, like some directions in the vector space that mean something like plural of words. So you can go from singular version into plural version. You can go from present tense of verbs into past tense by going in some different direction. So all you basically need is to just figure out what is this translation vector, and you can be changing the properties of the words by finding the nearest neighbor after the calculation. It works even for words that are kind of like not sharing any simple like regularities just by looking at them like this equation king minus man plus woman. We can just do this with the vectors and then do the nearest neighbor search, and we'll obtain actually many words that kind of make sense. And the first one is for models that are trained on large data sets. It's Queen, so it really makes sense. People can actually try this. I think there are some online demos when they can try these analogies on their own. This is another actually example, but that's coming for actually a model that we trained at Google in 2012, and it was after dimensional reduction using PCA, which is also unsupervised. So you just go from this higher dimensional word vectors into two-dimensional space, and then you plot the vectors, and it was looking surprisingly good. If you consider that you actually have to throw away much of the data by performing this dimensional reduction. And you can see that actually countries and capital cities got clustered somewhat together. So even like geographically, for example, like southern European countries are like Italy, Spain, Greece, Portugal are close to each other. But there's also like this translation vector between the capital cities and the countries. So the only supervised information in this picture is the gray arrows that we actually edit ourselves to show like there's like this general direction, and everything else was found unsupervisedly just by the neural network reading tons of data and updating the parameters. So of course, it's just nice for illustration. We wanted to actually get some numbers, like how accurate the models are. So we did put together this data set with around 20,000 of these analogy questions that are divided into several categories. Here are just a few examples. So actually, it's not completely easy. Like, for example, people have to figure out that like what is the currency that is used in Iran, which I think is not that easy example even for people. I think it was real. But for some other analogies, it's actually quite easy, like possibly, impossibly, that's going to be very easy. Just if you think, if you just also think of the neural network that has to do this task without actually looking at the word structure, but it just sees the word as basically entry in a vocabulary, that's actually quite surprising that it worked so well as it did. So here is one of the popular choices that were chosen by many people to train these word vectors like years ago, where people actually trained a full language model, full neural network language model, and then they did use just the word vectors, which is like this matrix U in the figure. So just to describe the model, it's coming from Yosha Bengio from 2003. It was like a very nice model that achieved state-of-the-art performance in language modeling back in the days. And here you have like 3 words encoded as 1 of n at the input layer, and then you have the projection layer, which is basically matrix multiplication by going from input layer to the projection layer. There you have the basically concatenation of these 3 word vectors, and after that you have a hidden layer with some nonlinearity and softmax. So what I basically did with the word2vec was, by looking at the model, you can actually see that yeah, if you care just about the word vectors and we'll be showing the other matrices, you can look actually where most of the training time is spent, and it's actually the matrix V, because for W there are some optimization tricks how to avoid the big softmax classification, but the matrix V have to be accessed fully for every training example, and that's actually like almost 100% of time is spent there. So what can you do instead is to simply remove the hidden layer, which will actually make the network unable to learn n-grams from the input, but it doesn't seem to be all that needed if you just care about the word vectors. So the architecture looks like this. You just take basically training sentences, and for each word you take as the input signals the words around this word that you are trying to predict, sum the word vectors and do the prediction, which can be softmax or some approximation of it, and then you apply a stochastic gradient descent and a backpropagation, which means that you will slightly change the weight so that next time you would see the same input features, you would make a somewhat better prediction. And that's pretty much it. It's a much lighter model than Bengio's model, and it scales much better, like to very large data sets that were used in companies like Facebook, Google, and so on. This is like the second model that we did propose in that original paper, but it works pretty much the same. It's just like, it can be easier for some other applications to use this one. It's the skipgram model, where we take the middle word and you try to predict the surrounding words. There are some differences in these algorithms, but they are not really that big usually. I think the best architecture usually is the continuous backup words, where we are actually summing the word vectors from the context and predicting the middle word. As I said, we trained it with like the most popular choice, which is like stochastic gradient descent and a backpropagation. And for the solution for the large softmax, there are like 2 simple tricks that we did support, which is like the hierarchical softmax that doesn't try to predict all the outputs, but basically just like some class-based approach. And even simpler one is to forget about the softmax at all in the output layer and just treat all the output units as independent predictors, and then we just sample a few negative examples and take the positive example and propagate gradients from these and ignore everything else. So that's called negative sampling. Here is the comparison of the performance. Of course, since 2013, numbers did get even better. I will show a bit later that we can train models even faster and on more data and so on, like as always. But back then, the difference was like extremely visible, like that you basically do not really need to train a full language model, and you can train on much more data, bigger models, and then you go basically from like weeks or months of training to minutes, and you will get even much better accuracy on these analogy test sets. Of course, like not surprisingly, what we did find is that more data and bigger models lead to better results, which I think is pretty much always the case in supervised machine learning. and probably even unsupervised. So here are a few more like funny examples that we did compute back then. So as you can see, it works interestingly, and that's why I said that people can actually try something on their own, because I think there are some online demos, or you can just download some existing models and play with them. Like I think the one with sushi minus Japan plus Germany is really nice, but yeah, it's kind of funny. We did spend quite a bit of time by just trying this because it was a lot of fun. But of course, people can be wondering, like, what are the next things? I wouldn't say that there was any fundamental breakthrough, although like many people did try to build better models than Word2Vec, but I think it's still pretty much the state of the art. We can somewhat improve accuracy by actually taking into account also like the structure of the word. So by using the character engrams that actually form the word as additional inputs when we are forming the input representation, we can predict the word with better accuracy and form even better representations. What is interesting about this approach is that we can this way also form representation for out-of-vocabulary words. So even words that the model was not trained on, for these we can actually compute the representations. So that's actually very nice if you, for example, have some application and you know that the users can for example, misspell words, that there can be some typos, and you want the system to be somewhat robust to this. So then actually building the representations based on all the word structure information can be very nice. So here is like the performance gain that we have on the analogy tasks. As you can see, for English, it doesn't really help that much. For German, it's slightly better, like 2 or 3% accuracy, but mostly you will gain better performance on these tasks on languages like Czech, because they are morphologically much richer, you have much bigger vocabulary, and usually you also have less data for these languages. But in the end, I think it's nice to try this for any language. Depends on what your application is. Here is comparison to one popular version of Word2Vec that's coming from Stanford that is called GLOV. It works very similarly to Word2Vec, just instead of seeing the optimization as some type of neural network, these guys did perform matrix factorization, but it's actually doing very similar thing. But in our comparison, we did basically find that despite the claims by Richard Socher and others, actually when we trained on similar data, then the original algorithm was actually quite a bit better, and fast text is even better than that. I think one problem is that actually training a really good model takes few tricks that people have to do well. It also takes few days to compute the best models, especially if you want to train something on the full web crawl, like hundreds of billions of words. And most of the people actually want to try to use just the existing word vectors. So for that reason, we also did publish this summer these models from this table, also trained on crawl, like different version on this fasttext.cc page, so people can use them easily. We also have supervised mode in the fasttext library. It's very simple, like it's like the CBO architecture that I was showing before, just you will not be predicting the middle word, but you will be predicting the label. That's for cases where you actually have the labels. Again, it's kind of interesting that when we did compare this simple model that's like very scalable, it can be trained on huge amounts of data, which is what we were considering as the biggest advantage. We did actually find that its accuracy is very similar, sometimes even better than of the fancy deep learning models, like that we're using like 10 hidden layers with some bidirectional STMs and so on. So I would say that when it comes to text classification, the deep learning techniques didn't really bring us much anything yet, and optimized architectures like fasttext are actually much better to be used in products because they are just much faster to be trained. You don't really need any expensive hardware like GPUs, and you can scale like to pretty much any size data sets, even on a single machine. Even if you are working in these big companies, it's actually a very useful tool, and it's used in many teams. That's for it. So summary is for this part is that for building text representations and text classifiers, it seems that simple and scalable models are the most useful in practice. The the best accuracy is usually achieved by the model that is trained on the biggest amounts of data, and that's usually the scalable models. It can be neural networks, but we don't actually have to overcomplicate their architectures, and we can be using pretty simple ones. For that, I would recommend people to look at the FastX library because it's very simple to use and already is very scalable for both the unsupervised and supervised classification. The second part of the talk will be about where actually the deep learning works for NLP, and that's for like modeling sequences of words. So that's tasks like language modeling, machine translation, and so on. Basically, where you have to deal with word order, where the word order is actually very important. It's not clear if you need a word order if you are trying to classify web pages, but if you want to translate sentences, that actually it's a completely different story. Then the word order is actually much more important. And I will describe my story, like how I got to these models somewhat and what results I obtained and how it evolved since. So the simple architecture was used for by quite a few people in the late 80s and early 90s. It was looking kind of like this. You have like the input layer that's encoding the current symbol. You can see the current word. Then you have the hidden layer. And then you have the prediction of the next word. And you get the time here by conditioning the state of the hidden layer on the state of the hidden layer from the previous time step. So there's this recurrence. So the network is basically sending the state of the hidden layer into the future states of the model. So there's this loop. That's why we call them recurrent. And it was like a very nice model. But except some toy tasks, people couldn't really train it very well back then. And there was even a paper that did convince a large part of the community that these models are really unstable to be trained by SGD. And people were looking at more like complicated ways how to train them. And when I was a student myself, I didn't really see much like any papers on recurrent networks. There were like papers on LSTMs coming from, for example, ETSIA. But even there, like when I wanted to work on these techniques as a student, like my advisors were not supportive at all. They said that basically there's like too much complexity and nobody really knows how to implement these models. And the papers that were published at conferences were not competitive with much simpler techniques. So there was like a lot of skepticism about recurrent networks back then. But it was possible to actually overcome this. And surprisingly, there was nothing mysterious that was needed. Again, it was the same story, like big models and a lot of data, optimized implementations that are scalable and fast to be trained. There was like one novelty that I did develop like in 2010, and I think that that's the reason why many people did observe this instability of the training in recurrent networks and why their results were not good. And that's basically the gradients can be sometimes very infrequently they can be getting exponentially larger as you are using a backpropagation to time algorithm, and you can do pretty much anything, like for example clip the gradient so that they stay in some range or even discard these training examples. But people have to do something about the exploding gradients to keep the training stable. Otherwise there's like this jump in the weight space and the network pretty much forgets everything that it learned before because it just jumps into some strange mode and it can even completely diverge. So I think that was important. And another thing that I consider very important looking back is that many people actually didn't really know how to implement the recurrent networks, and they were like not very good public data sets. So I did publish this toolkit together with the Pantry Bank, like one version of the Pantry Bank data set for language modeling, and I think that convinced a lot of people from the industry because they were able to reproduce the experiments quite easily. So here are just a few results, how it went back then. There's like a very famous setup from the speech recognition community. It's the Wall Street Journal ASR setup. And it wasn't really state-of-the-art in 2010, but the main thing here was that if you change the language model from what was considered state-of-the-art in 2010, which was basically 5-gram with modified Netherlands smoothing, And if you rescore the hypothesis produced by the speech recognizer by the recurrent networks, where basically here all the lines are basically just bigger and bigger models, then you can see that by using ensemble of big models, you can get like a more than 20% reduction of the word rate, which was considered pretty huge for just a change of language model. Here was like another figure that did convince back then people that these models may be not completely hopeless, and there was this figure that's showing that the more training data you use, the bigger is the gain over the n-grams, which is completely the opposite of what people observed for the class-based models that usually work just when you have small amounts of data, and then the gains are getting smaller and smaller, and then they vanish. So people were convinced that actually it's not possible to beat n-grams at all. So it was completely different with RNNs, and RNNs are just getting better the more data you use. Even like the gap is getting bigger. Here was the strongest setup that I used for speech recognition experiments. It was coming from IBM. It was based on their Attila decoder, and it was sort of like a very strong setup that the company did work for like 10 years or so. And even here we did obtain very nice gains. Basically in the figure, the green line is the baseline, which is the foreground model. And then if you look at the lines, it's basically like the models are getting bigger and bigger, and the word rate is getting smaller. In the end, by combining 3 of the biggest models, we did get to like 11.7% error rate, which was 11% relative reduction of the word rate, and that was like a great result back then, because it was like on this very strong setup. Then I also tried to apply these models to machine translation, and again, it was very simple to actually get good results. It was just n-based rescoring, but I could get up to 3 blue points over the best setups at Johns Hopkins University. And it was, again, like very similar for data compression. And even here I have a fun example. People can see that one of the arguments against statistical language modeling that was kind of famous is coming from Chomsky, who did claim that talking about probability of sentences makes no sense because you can actually form a sentence that was never said before, but still can have some reasonable probability, and then he can form a sentence from the same words that actually makes no sense at all and should be considered by completely improbable. But his claim was that n-grams, or basically statistical models, will not be able to learn this probability correctly. It's actually true for n-grams, as you can see. The n-grams are not able to distinguish which of these sentences make sense because all the bigrams are unique anyways and were not seen in the training data. But for RNNs it's different, and they assign like 100,000 times higher probability for the word for the sentence where actually there is like some syntactic structure. Of course, I should warn also, like so that the hype doesn't go too big, that RNNs don't really understand the language. What they are doing here in this example is that they are clustering the sequences. So they see that, for example, if you have a verb and then some other word, then that's more likely than having some other combination of the words. So that's basically the logic why the RNNs are able to figure out what sentences make sense and what not. Of course, like this is also the reason why RNNs are producing much more readable output. We did see, for example, in the previous presentation, some machine translation examples, but that's exactly the same for speech recognition. There are other applications that if you generate text from RNNs, then it's looking way more natural than from n-grams. It's actually true, especially for languages that are morphologically rich, like Czech, for example. Google Translate used to work terribly for translation from English to Czech, but this year that Google did switch to neural-based translation, it's actually much more fluent. So it's finally useful. And okay, back to this. So for the history of recurrent network language models, I think, or recurrent networks in general, I think these models are much more easy to work with today because there are many open source toolkits that implement RNNs, and people don't have to code them themselves. There's like a TensorFlow that we did hear about. There's also others like Tiano and Torch and PyTorch, and I think like maybe 10 others. But it's all great that all these companies are supporting open source toolkits, and also like the other part of the success is that there's a lot of open data sets that people can be using, so that it's easier to compare experiments and it's easier to see which techniques work and which are not really bringing much. So this is quite a bit different than like 10 years ago, when most of the data sets were like very expensive and just accessible by researchers from universities, and everybody was publishing results on like their version of these data sets, so nothing was comparable at all. And the other exciting thing is the scaling to much larger data sets thanks to GPUs, because for recurrent networks, the story is a bit different than for Word2Vec or FastText. We still need the matrix multiplications in these models, and then actually the GPUs are bringing us very nice speedups. And today, of course, we have like tons of applications. If there's some trend, then it's definitely like moving more to end-to-end systems to like solve the whole task using neural networks and not even combine them with some other systems as it used to be done, like when these models were like 100 times or 1,000 times smaller than is common nowadays. Maybe there's some downside that I feel with all this open sourcing and so on, that the hype is getting too strong, and people are using RNNs for tasks where they are too powerful. As I was showing example with FastText, when you are doing supervised text classification, then in many cases, probably in most of the cases, just simple model is fine, and you don't need recurrent networks to be able to, for example, do classification of sentiment or something of that sort. It may be actually much better to spend your time on getting more training data than trying to develop some magical architecture. Also, I think that some people are like making the hype worse by overstating what these networks are, like saying that RNNs or LSTMs are like the brain is like a huge overstatement, and I wouldn't really trust people who make these claims. We did actually show that I think that the LSTMs are very popular, for example, now as special architecture of RNNs. That's a bit complicated. We will probably hear a bit more from Seb in the next talk about them. But we did show that basically for these language tasks, we can understand very easily what these models learn. It's basically some sort of cache that they can learn some sort of like summary of the recent history of, say, like last 50 or 100 words. It's the same as the idea from like the early 90s that was called cache models. Later, very similar models used to be called topic models. So people often like reinvent the same idea. What's nice about LSTM is that you have the cache directly in the RNN architecture, but there's actually simpler way how to get the cache information, and that's a small modification of the simple RNN, where you can just make part of the recurrent layer to be diagonal and few more small tricks, and then you basically get the same performance from simple RNNs as from LSTMs without the complexity. We did describe it in detail in this paper, Learning Longer Memory and Recurrent Neural Networks. So for people who are interested in this, they can have a look. And I think it can explain very nicely what the more complicated architectures are actually learning for in the NLP tasks. So for the summary, I would say RNNs are not really like the brain. They are just clustering sequences. Basically what Word2Vec does for words, recurrent networks do for sequences. So they can like place similar sentences into similar space. So the hidden layer representation will be similar. And through this, they can generalize better than techniques like n-grams that actually increase number of parameters with the length of the context exponentially, because they can't do any parameter sharing. N-grams were like state-of-the-art for like over 30 years, and were considered even like unbeatable by many people. I remember like when I was working on my PhD thesis, people were like desperate and were not really hopeful at all that it's possible to beat n-grams, because all that people did believe back then was just bigger training sets and simple n-grams. But it wasn't true, and now many of the NLP tasks have like state-of-the-art performance with using recurrent networks. So from my point of view, for the summary, for the paradigm shift, I think the open source tools, public data sets, and easy reproducibility was completely crucial, so that there would be this RNN revolution that happened in the last 5-6 years. Then the gradient clipping was completely essential, otherwise these models diverge, and nobody who I did talk with back then did know about this technique. So I think it's also very important. And then I think the results that were achieved on like standard benchmarks that convinced many people from academia and industry, which was also completely crucial. So that's the end for this talk. I will not be talking really about any complicated things like what we plan to do next, but I would definitely say that we don't think that we can solve artificial intelligence by just recurrent networks, and we have like some other projects like the communication-based artificial intelligence that people can look at, where we are trying to define much less supervised problems that can be motivating people to work on even like more powerful models in the future. So thanks for the attention, and we can go for questions.
Thanks, Thomas. Well, I tried to put up the Slido wall. Where is it? Yeah. I would like to add two thoughts. For one, organizations sit on top of tons of text data, and they don't even realize that it's actually data. And so this is why this research is also so exciting, because it kind of helps in making it put calculations on top of the text data. And the second thought is it's like you can use those pre-trained models and get started quite easily without even the need to understand all the math behind it. So many thanks, Thomas. There were, I will pick the first one. How can word2vec disambiguate words like queen from royalty and queen the music group? Are they both mapped to the same word vector?
Well, in this example, probably you can just say that the words are different because they have like a uppercase character and lowercase character, but okay. Okay, normally you can actually do this disambiguation, and actually we did this back like in the days at Google too, and it's a quite simple solution. You can be doing this disambiguation based on the context. So to give an example how to compute this, it's basically two-pass algorithm. First, you compute just the normal word vectors with single sense, and then you will try to measure the number of senses of each word by computing the representation of the context, which is basically the sum of the word vectors from the context, and performing k-means clustering. The simplest algorithm can be that you just pick 3 senses for each word as a hard limit, and you will not even try to learn the k. And this way you actually annotate the data again like with the word senses and retrain another model that has this sense of the word. I did even describe it at the word2vec discussion forum if people want to look at it. The implementation is quite simple. I'm not sure if somebody did make public the code for this, but it's quite easy to implement it. So the main idea is really that you are doing the disambiguation based on the context, because queen, for example, will, like in the first sense, will probably appear in the context of like say king or some name and so on. But queen as the music group will appear in the context of some like musicians and names of songs and so on. So you really need just the context to figure out what is the word sense.
Okay, thank you. I will pick just the next one. What do you think is the most interesting unsupervised learning problem where deep learning can be used?
Most interesting. Yeah, I will have to think about it. Well, of course, I would say text is the first response, but then it's hard to say whether there are techniques like word2vec are deep learning, because they are more like machine learning. There's not really much depth about it. I also think that there is some shift about the naming of the algorithms, like what used to be called deep learning 5 years ago is somewhat different than what it is today. But back to the question, most interesting unsupervised learning. Actually, there's very interesting work that's done on the unsupervised learning of image features. nowadays, many people, for example, know about like techniques that are, in my opinion, somewhat overhyped, that are based on the generative adversarial networks, but they are even simpler techniques that do not require any complicated math and that can learn actually better unsupervised, better features for images in a completely unsupervised way, so without any labels, and that are based on like simpler approaches. If I remember correctly, it was like published this year by some people who are working at Facebook, a research team, Piotr Bojanowski. I think it was noise as training or something of that sort. I think people can find it. So I think this is pretty exciting because there you can see that you can learn representations from like ImageNet like very nicely, even when nobody gives you any labels.
Thank you. Are there questions in the room that we want to pick? Maybe there's one.
Yeah, I didn't understand a whole lot of what you were talking about. So my question was this: you mentioned vector accuracy of a word. Could you maybe define what you mean by that?
The accuracy was in that analogy data set that I was showing. Basically, you have like 20,000 of these analogy problems, and you try to compute the answer. Maybe if I can go back to the slides. I have no idea. Yeah. It was at the beginning. So, for example, you have here, like, imagine that you have 20,000 of these examples, and your task is to compute, for example, equation of the type like Greece minus Athens plus Oslo, and then you do the nearest neighbor search in your vector space, and of course you are using your existing word vectors for this task, and then we compute the fourth word, and if it's Norway, then it's correct, and if it's something else, then it's incorrect, and this way you compute accuracy on these analogies. So if you will use better, more regular word vectors that were trained, for example, on more data or with better algorithm, then actually what we observed is that accuracy on these data sets is getting up, and if you use, say, less data, or you run less training epochs, or you use smaller models or lower quality data, then the accuracy goes down. So it actually turned out that this sort of data set is like very nice to see how good the model is.